So now that you collected all this data regarding the centripetal force, what are you going to do with it? That's what the purpose of this video is to show you. And what you can see here is a little rendition of what you had. This is the weight hanging from a string, and this is the pole that was rotating. This is the counterweight, and this is the string I was pulling. So this thing was rotating something like this. And what you did, hopefully, and in looking at the videos, is you picked several of them. You counted the time it takes for 10 rotations. You divided that number by 10, and that'll tell you how long it takes to go around for one rotation. And that's something called the period, which you'll see. It's capital T is the period. Okay, so that's what this is about. And what are the forces that are occurring here? Well, because this was vertical, that made it really convenient. That means that gravity and tension should be equal and opposite, because those are the only two forces acting in the vertical direction. They should be equal and opposite, so we can ignore those. The net force is really only the force caused by the spring here, or the rubber band, depending on which case you used. So, going to just a little bit further over here. I hope we can see this. This net force, this force of the spring, since that's the only force, it has to be equal to the mass times the acceleration. But since it's an object moving in a constant circular motion, the acceleration should be the speed squared divided by the radius. And we know what the radius is. Those are the measurements we took, the 40.5 centimeters, the 37.5 centimeters, the 34 centimeters, or the 31 centimeters. Those are those distances we measured. And the force of the spring is the force that I measured with the vernier force probe. That was the last thing I did in the measurement phase. Okay, so that is that force of the spring, which was 4.6 newtons or 4.1 newtons, whatever it was. That was based upon the stretch of the spring. So I have all of the data here. I repeated them earlier, but I wrote them on the board so that I could see them. And so what your goal is to take the force of the spring that you measured, or that I measured with the vernier, and compare it to the mv squared over r for each of the cases, where m is the mass of the hanging bob. I'm going to have to give that to you. That's the goal of this lab, and then to basically find the percentage error between these two numbers. That's what we're trying to compare. So the mass of the little hanging object was 113 grams. You'll need to know that. The other thing you're going to need to know is that the period is going to be a function of how quickly the object was turning. So in one case that I looked at, I'm going to do an example problem for you here so you can see what I'm looking for, and you can do it on the other ones. On one of the ones that I looked at, I just measured one of them out of the 5. I expect you to measure all 5. But I measured that it took 6.5 seconds for one of the cases with the 31 centimeter radius to spin 10 times. So that means if it took 6.5 seconds for 10 spins, how many did it take for one spin? Well, you take, assuming it's spinning at a constant velocity, which was the goal, then I would take 6.5 seconds and divide it by 10 revolutions. And that gives me 0.65 seconds per revolution, or that the period in this case is 0.65 seconds. That's what's meant by the period. How long does it take to go around once? Clearly it's going to be different for every situation we looked at. Once you have the period, we can use that to figure out how fast it's moving. And this is a lot like the problems we did in orbits, where the speed of the object is going to be equal to 2 pi times the radius divided by the period. Here's the situation. You're going around in a big circle like that. That takes 0.65 seconds to go around once. The circle of radius r. What's the distance there that it goes around? Well, it's 2 pi r. So the speed here is going to be equal to 2 times pi times r divided by the period. So for this case, the radius was 31 centimeters for the case where the period was 0.65 seconds. So that's the r I'll plug in there. All right, so if I do that, I'll plug in 2. I'm going to erase this other stuff here. I have 2 times pi times 0.31 meters divided by the period of 0.65 seconds. And if you do the math, which I did do, you're going to get something about 3 meters per second. Make sure you can see me. I'm going to shift this a little bit over to the right. Okay, 3 meters per second. That's what that number is. Okay, and 3 meters per second, I can relate that to the centripetal force, because the centripetal force, which is also going to be equal to the spring force, or the spring force is the centripetal force. It's equal to the mass times the acceleration. The acceleration is equal to v squared divided by r. That's our v. That's how fast the object's moving, 3 meters per second. So I take 3 squared divided by my radius of 0.31 meters, multiply this times the mass. So if I take mv squared over r, multiply this times 0.118 kilograms, which is 118 grams, what does that give me? Well, it gives me, I think, I just did it in Excel, did it over here in Excel, and I have 3.28 newtons. Now the question is, what was the force that I measured for the spring for this? What was the force I measured for the spring? It was 3.1 newtons. So I was pretty close. So then you can find the percentage error. The other thing that's asked for in this lab is some measurement of the uncertainty. And to do that, you have to, one way to do that is, since you have 5 different measurements of the period here, I just took one of them, you're going to get an average and a standard deviation. You can measure what the standard deviation is. You can look at some, let's say the period is 0.65 seconds and the standard deviation is 0.1 or something like that, 0.1 second. You could say, well, the period's somewhere between 0.55 and 0.75 seconds. And so you can compute a range of values that this centripetal force might have had. 3.28 newtons might be the average, but it might have been as low as 3 newtons and as high as 3.6 newtons. That gives you a range of uncertainty, and that's the other thing that this lab's looking for some calculation, some idea to try to measure that. Kind of like in the M&M lab that you did in the beginning of the semester, that's what we're looking for here. Can you come up with some, yes, there's the percentage error, but can you come up with some other measurement for an uncertainty, a range of values that this might have been based upon the precision of your measurements? Okay, good luck with this lab. There's a lot here, and I like the lab in that you can actually get numbers that hopefully should work out certainly within 10% error, maybe even a lot less than that. Okay, good luck. After I finished the video and took a quick look at it, I realized you didn't see the bottom of the board. So that's where it is. That's the calculation of 3.28 newtons. And here's the way I calculated it. It's mv squared over r. So you should get something like that for one of the cases, and then hopefully other numbers for the other cases that come close to matching the force that you measured on the vernier force probe with the spring.